this section, I'm going to talk about curve sketching polynomials. Suppose you were asked to graph this function, x squared minus 4x plus 4. All of these problems involve 8 steps. 4 for the first derivative, and then the same exact 4 steps for the second derivative. So first step is to find the derivative and then factor it. The second step is to find out when it equals 0. It equals 0 when x is equal to 2. The next step is to find the corresponding y value. So it's going to be 2 squared minus 4 times 2 plus 2 is 4 plus 4 is 8 minus 8 is 0. So you have a critical point at 2, 0. Now let us find their second derivative. Let's call it f1 prime. So f double prime of x is equal to 2. And this equals 0, never. So for 3 prime and 4 prime, you don't have to do anything because we didn't find anything in the earlier steps. And one last step is to calculate f for 0. It's going to be 0 squared minus 4 times 0 plus 4, which is 4. So we get 0, 4. Okay. Now we make up our table. Let's try to pull off the table here. So the first thing you do is you write down all the values that made the first derivative 0 and the second derivative 0, which is only 2. And if there were more, you put them in increasing order. So we're going to go from negative infinity up to 2, and then from 2 to infinity. The only number that isn't in one of those intervals is 2. And if there were other critical points, it wouldn't include those values as well. Now, we want to look at the plus minus sign of the first derivative. Now, the first derivative is 2 times x minus 2. Well, 2 is always positive, the first factor, and the second factor is only positive. X minus 2 is only positive if x is more than 2. And it's negative when x is less than 2. So the overall sign is negative in the left interval for the first derivative and positive in the second interval. Now, f double prime of x is always 2. And 2 is always positive. So what we know from this is, first the function is decreasing, because it says negative, and then is positive, that means it's increasing. And it's always part of that. It is concave up. Okay, so we plot all the points of interest. 0, 4 came up, and when x was 2, how much was y? I think it was 4. No, when x is 2, y was 0. Okay, so when x is 2, 1, 2, 1, 2, y is 0. X, y-axis. First, I come down to 2 down here, and then I go up. That I know from the first derivative. The second derivative tells me I'm always concave up. There's my graph. So it's not the dotted graph, but it's the bold one. You want to erase that? Go for it. But it definitely helps you. Let us try another one. Suppose f of x or y is x to the 4th minus 12x cubed plus 48x squared minus 64x. Well, the first derivative then is 4x cubed minus 36x squared plus 96x minus 64. Now we factor. Can factor out a 4. We get x cubed minus 9x squared plus 25, right? So then 24x minus 16. And you can use the rational root test, but I noticed that 1 plus 24 is 25, and that negative 9 minus 16 is negative 25. So if x is positive 1, this will be 1, and that will be 24 for a sum of 25. And if x is negative, it'll be also minus 25. So I know that x equals 1 is a factor. The x minus 1. Now, how do you find the other factor? You can try synthetic division. You have 1x cubed minus 9x squared, 24x's minus 16. And that's 1 when x is 1. I like to put a 0 here. You add, you get 1. You multiply, you put the answer there. You add, you get negative 8. Negative 1 times negative 8 is negative 8. You add, you get 32. You multiply the 1 into 32, and you get 32. So let me just see what's going wrong here. 9 minus 8. Oh, excuse me. 18 minus 24 minus 8 is 16. Excuse me. 1 times 16 goes there. I add, I get 0. Just like I should. This tells me the other factor. It's x squared minus 8x plus 16. Okay, so it's 8 squared minus 8x plus 16. Now, can I factor that one? The answer is yes. Half of that number is negative 8. Is negative 4. And when I square that, I get 16. So it's x minus 4 squared. Okay, so I'm going to erase this side work. And we're going to say that this equals 0 when either that's 0, or that's 0. And this is never 0. That's 0 when x is 1. And that's 0 when x is 4. Okay. What are the corresponding y values? Well, when you plug in 1, you're going to get 1 minus 12 plus 48 minus 64. So 1 plus 48 is 69. It's 49, excuse me. And if you take away 12, you get 37. If you take away 64, you get 27. Negative 27. And now if you plug in 4, it's going to be more involved. You're going to get 4 cubed minus 12 times 4 cubed. So, excuse me. The first one's going to be 4 to the 4th, of course, minus 12 times 4 cubed, plus 48 times 4 squared, minus 64 times 4. Now, there's lots of 4's in here. So this is 4 to the 4th. 12 is 3 times 4. Times 4 cubed is 4 to the 4th. 48 is 3 times 16, which is 3 times 4 squared, times another 4 squared, that's plus 3 times 4 to the 4th, and 64 is 4 times 4 times 4 times another 4, which is 4 to the 4th. Okay, so how many 4 to the 4th do I have? I have 1 here, I'm taking away 3, I'm adding 3, and then I am taking away 1. Let me try that again because I wrote down one number wrong. Over here, I have 1 4 to the 4th. I am taking away 3 of them. I am adding back 3 of them. And now, at the end, I'm taking away 1. That's 0. Notice, please, I never even found out what 4 to the 4th is. Sorry, 4 to the 4th times 0 is 0. Okay, so when x is 4, y is 0. That's another point. Okay, this here was side work. Now, let us find the second derivative. The second derivative, well, it's going to have the 4 already factored out. Why take it from here? Let's take it from here. So it'll be 3x squared minus 18x plus 24. Well, I can factor out a 3 from those numbers. Times it by the 4 in front gives me 12. So I have x squared minus 6x plus 4. Or can you think of two numbers that multiply out the 4 and add up to negative, that should be 8. Can you think of two numbers that multiply out to 8 but add up to negative 6? I can, and I'm going to put those numbers next to the x's. How about negative 4 and negative 2? So the second derivative equals 0. Well, that factor is never 0. That factor is 0 when x is 4. And I already know the y value there. I got it from over here. And when x equals 2, well, it's going to be 2 squared minus 12 times 2 cubed plus 48 times 2 squared minus 64 times 2. Okay, all right. So, of course, once again, don't know why I keep calling that 2 squared. So it's 2 to the 4th. Now, I notice I can get another 2 out of here, so that'll be 2 to the 4th. I can pull 2 squared out of here, that's 2 to the 4th. I can pull an 8 out of here, which is 2 cubed, times that is 2 to the 4th. So I just have a number of 2 to the 4th. Here I have 1. Now this number here is 2 times 6. Because I need one more 2. 2 times 2 cubed, that's 2 to the 4th. I factored that out, minus the 6. This number here is 12 times 4. 2 squared is 4. Times another 2 squared, that's 12 times 2 to the 4th. Minus this here is 16 times 4. That is 16 times, oops, I want 8. This happens to be 8 times 8, and the second 8 is 2 cubed, times the 2 squared. That gives me 8 2 to the 4th. Okay, 2 to the 4th happens to be 16. And I'm dealing with smaller numbers now. 12 minus 8 is 4, plus 1 is 5, minus 6 is negative 1. Minus some silly error, I get negative 16. So y is negative 16. Now we are ready to make the table. I write down the x values that made the first derivative 0. I write down any new values that made the second derivative 0. I don't have to write 4 again. And then I put them in order, 1, 2, and 4. So when it comes to the table, I'm going to go from negative infinity to the first number, and then the first number to the second number, and then the second number to the third number, and then finally the third number all the way to infinity. And my goal here is to find the sign of the first derivative and the second derivative in each of these intervals. And the chart tells you everything. Now, the first derivative, well, the second derivative happens to be in front of me. So let's write it down. It's 12 times x minus 4 times x minus 2. Let's put it to the left some more, and let's write it nicely. So the second derivative is 12 times x minus 4 times x take away 2. And the first derivative happens to be this here, 1 and 4 squared. So it's 4 times x minus 1 times x minus 4 squared. Okay. Now, notice that x is never 4. It's never 1, it's never 2, and it's never 4. So this is always positive. And 4 is always positive. It's the middle term that changes. If x is more than 1, that is, when is x minus 1 positive? Well, add 1 and you find out. That's when x is bigger than 1. Only this interval, and that interval, x is bigger than 1. To the right of this line, x is bigger than 1. To the left, it's negative. So you multiply those three signs, you get a negative, a positive, then a positive. The graph comes down because it's negative, then it goes up, and then it goes up, and then it goes up. Now we look at the second derivative. 12 is always positive. X minus 4, when is it positive? You should know it's when x is bigger than 4. How much money you have to have in the bank so you can take out 4 and have something left over? You have to have more than 4. Well, only this interval to the right of that line is positive. The other ones, x's are all less than 4. When is x minus 2 positive? Well, when x is more than 2. That happens to the right of this line. So I put positive to the right and negative to the left. The overall sign is positive, positive, negative, and positive. So is concave up, is concave up, is concave down, is concave up. The signs for the second derivative changed here and here. That means that at 2, we have our point of inflection. At 4, we have a point of inflection. Wherever the first derivative changes signs, we have a point of inflection. Now, over here, I'm going to put all the points that came up. I guess there's 3 of them. There's a point where x is 1, there's a point where x is 2, and there's another point when x is 4. When x is 1, we get negative 27 and 0. Negative 27 and 0. When x is 2, over here, we got negative 16. Okay, so now, one more point. When x is 0, get that x-intercept. When x is 0, it's going to be the constant. There is no constant. That is, the constant is plus 0. X to a power is 0. X to a power times, 0 to a power is 0. 12 times 0 to a power is 0. 48 times 0 squared is 0. 48 times 0 is 0. Add, subtract them, you get 0. Okay, so it crosses the origin. All right, so now we plot these 4 points. And since most of the x's that we came up with are positive, I'll put the y-axis a little bit more to the left. So we have 1, 2, 3, and 4, and the x-axis. When x is 1, I bottom out at negative 27. When x is 2, I go down a little bit more than halfway. I go to negative 16. When x is 4, I'm at 0. And I cross the origin. Okay. Now, what happens? Let's look at the first derivative. So, up to 1, from negative infinity to 1, I'm decreasing. So 1 is way down here. And I have to cross the origin. So I am decreasing. After 1, that is from 1 to 2, I am increasing. I have to cross there. And then from 2 to 4, I'm increasing still. But I have to cross here. And then after 4, I'm still increasing. Okay. Now we'll put the concavity in between negative infinity all the way up to 2. I am concave up. So I would draw it this way. Concave upward. Nice U shape. After 2, from 2 to 4, I'm concave down. So I go like this. And then after 4, I'm concave up. I go that way. Remember, concave up is also that way. Why didn't I go that way? Because the first derivative was positive. I had to go up. If the first derivative was negative after 4, then I would have gone down. Okay. And there is your graph. The table tells you everything. Let us try another couple of problems. We'll actually do the next one twice. Suppose you have y equal x cubed minus 3x squared plus the number 3. So y prime is 3x squared minus 6x. I'll factor out as 3x. 3x times x gives me 3x squared minus 3x times 2 gives me minus 6x. Now, this equals 0 when one of these 3 factors are 0. When x is 0 or when x is 2. Let us find the y values. For a polynomial, when x is 0, the y value is always the constant. So we have that point. When x is 2, you get 2 cubed minus 3 times 2 squared plus 3. You get 8 minus 3 times 4 plus 3. 8 plus 3 is 11. Take away 1 more than 11. You'll be at negative 1. Okay. Now, we do the same thing for the second derivative. Probably the best form to have the first derivative in is not complete factored form, but just factor out the common number, no x's. So that's the first, that's when you have to do it correctly. Let me be sure. That's the first derivative. Ready to take the second derivative. So the 3 stays there. The derivative of x squared minus 2x is 2x minus 2. Factor out the common 2. When you multiply it by 3, you get 6 times x minus 1. Now this equals 0 when x is 1. And the y value will be 1 minus 3 plus 3. Well, the minus 3 plus 3 cancels out, so you just get the 1. 1 minus 3 plus 3. You have some money in the bank. I don't care if it's $1 or $1 million. If you take out 3 and then you add the 3 back, that cancels out. In this case, you have 1. Or if you started with $1 million and you take out 3 and then you put it back, there'll be $1 million. I mean, suppose, there's some money on the table. You don't know how much it is. And you come over and you take $3. And then you feel really badly and you put this $3 back. Well, you're going to have what you started with. Okay? Or maybe you have some money in your pocket and you take out $3 to buy an item. And then you say, you know what, I'd rather not spend the $3 on an item, and you put the $3 back in your pocket. Whatever you had at the beginning, that's what you're going to have at the end. Okay, so we found when the first derivative equals to 0 and their corresponding y values, and when the second derivative was 0 and its corresponding y values, the next thing I would do is I would find out what you get when x is 0, but we happen to already have done that. Okay. Now, before we make up our table, we list down all the x values that came up from the first or second derivative equaling 0. Not because we wanted to find the x-intercept. Actually, the y-intercept. I apologize. And then we put them in order. The order is 0, 1, and 2. So then what we do is we make up our tables, 0, 1, and 2. The table is going to go from negative infinity up to the smallest value, which is 0, and then from 0 to 1, and then from 1 to 2, and then from 2 to infinity. And we want to investigate the plus minus signs of the first derivative and the second derivative. The second derivative happens to be right here. F double prime of x is 6 times x minus 1. And the first derivative is, well, it is what it is. The first derivative, we're going to look at it like that. 3x times x minus 2. 3x times x minus 2. Okay. Well, 3 is always positive. X is only positive if x is positive. That means greater than 0. That happens to the right of this. It's always positive. and to the left it's negative. And x minus 2 is only positive when x is bigger than 2, which is only this last interval. Positive, and all the others are negative. The overall sign is positive, negative, negative, and positive. I just multiply a positive times a negative is a negative, times the negative is a positive. A positive times a positive is a positive, times the negative is a negative. Positive times positive is positive, times the negative is negative. Multiply 3 positives together, you get positive. Or, you can just look at how many negative signs there are. If there's an even number of negatives, it's positive. If there's an odd number of negatives, like 1 is, it's negative. 1 negative, odd, negative. 0 negatives, 0 is even, so it's positive. Okay, second derivative, 6, always positive. You may say, it's a constant. Why do you include it? Because if it was negative 6, it wouldn't matter. Okay, x minus 1 is positive only if x is bigger than 1. But bigger than 1 occurs to the right, because there's 1 and bigger. So it's positive if we're bigger than 1, negative otherwise. Negative, negative, positive, positive. So it's concave down, concave up, concave up. It changed concavity at 1. Just want to point out something in the last graph. The concavity changed from positive, actually changed twice. It changed here, and then it changed here. So it changed at, well, I listed it. It changed at 2 and 4. And look, to the left of 2, the graph is concave up. Between 2 and 4 is concave down. And then after 4, it changed again. Looks good to me. That's what we said would happen, and that is what happened. Okay, so it only changes at 1. So we're going to have a point of inflection at x equal 1. Okay, let us plot all the points that came up. Let's move this up a drop. We have things going on when x is 0, and when x is 1, and when x is 2. Now, what are those points? When x is 0, what did we get? When x is 1, what was the y value? And when x was 2, what is the y value? Okay. All right, let's do it this way. So we have 0, 3, and 2, negative 1. 0, 3, and 2, negative 1. And for the second derivative, we came up with 1, 1. Okay. Let us plot these points. And then everything's fine. Except, let us have a much bigger graph. So we have 1, 2, 3. Let's label it. 1, 2, 3. Let's label it. So we have 0, 3, which is up here. We have 1, 1, which is right there. And then we have 2, negative 1, which is here. Now, what happens? Between negative infinity and 0, the slope is increasing. So, from negative infinity to 0, it's increasing. So, I come up like this. Well, let's get rid of this nonsense. Now, what happens after x is 0? After x is 0, from 0 to from 0 to 1, it's decreasing. Ooh, looks right to me. It's decreasing. I mean, how else are you going to get to this point here? And then from 1 to 2, it's still decreasing. And then after 2, it's increasing. Okay, now concavity all the way from 0 to 1 is concave down. So here's 1. So the graph is concave down. It's going to go like that. Now after 1, from 1 to infinity is always concave up. Okay, and of course I hit the points that I'm supposed to hit. Now the concavity changed right there at 1. To the left it was concave down, to the right is concave up. But that's exactly what we said we would get. Okay, we're not going to bother to find the x-intercepts. But finding the y-intercept is easy. Just plug in 0. Now, I'm going to show you another way of doing this problem. I'm going to derive a formula for a cubic. This is only for cubics. A general equation of a cubic is ax cubed plus bx squared plus cx plus d. Now, we want to find out the first derivative and where it's 0. Well, the first derivative is 3ax squared plus 2bx plus c. Oh, that's a cubic. Sorry, that's a quadratic. I know the formula for a quadratic. This equals 0 when x is equal to negative b. Now that's a, that's b, and that's c. It's negative b plus or minus the square root of b squared, 2b squared, minus 4 times a, which is 3a, times c, which is c. 3a and c. And all of this is divided by 2 times a. This is where you have critical points on a cubic. Let's clean this up a little bit. So we have negative 2b plus or minus 2b squared, well that's 4b squared, minus, I'm going to leave the 4 as it is. I'm going to multiply by 3ac all over 6a. Now, the reason I left the 4 where it is, so let me just write this down. The reason I left this 4 is because now I can factor out a 4. That is, what's underneath the radical is 4 times b squared minus 3ac. But this 4 can come out in front as a 2. So I have plus 2 plus minus 2 b squared minus 3ac. Now I can factor out a 2 from the whole thing. There's the 2. So I have negative b plus or minus the square root of b squared minus 3ac all over 6a, which is 2 times 3a. So these 2's will cancel. And here it is. Negative b plus or minus the square root of b squared minus 3ac over 3a. This here is the x value of the critical points for a cubic equation. Now, this is how I remember this formula, and I'll never forget it. As long as I remember the quadratic formula, I'll never forget this. And here's how I remember it. 4 and 2. What's the number in between 2 and 4? 3. Notice this formula is exactly this formula over here, except instead of where the 4 is, we have a 3, and where we have the 2, we have a 3. There they are. Instead of 2, we have a 3. Instead of 4, we have a 3. I just remember, oh, and in the quadratic formula, there's only 2 numbers, 4 and 2. The cubic, for the cubic equation, not the cubic formula. For the cubic equation, the critical points just, it's like the quadratic formula where you replace the 2 and the 4 with the 3. Now, where did we have the first derivative? Here is the first derivative. I'm going to copy it down. The first derivative was 3ax squared plus 2bx plus c, right? Yeah, plus c. Well, let's find the second derivative. That's where you find their points of inflection. Bring down the 2, you get 6ax plus a constant times x. The derivative is just the constant. And you set the second derivative equal to 0. Well, if I divide both sides by 2, I get 3ax plus b is 0. Bring the b over. I get 3ax is negative b. And then I divide by 3a. And you know what? Check this out. Oops, over 3a. When it comes to the min or max of a quadratic, it's that x equals negative b over 2a. Well, once again, the 2 becomes a 3. Okay. So now, the 2 becomes a 3. So we have these two formulas. So let us do this problem with that cubic all over again. And you decide if you like it. Actually, the cubic equation that we just drew was y is equal to x cubed minus 3x squared plus 3. Now, the formula says the x value for the critical points are at negative b plus or minus the square root of b squared minus 3ac over 3a. Okay, that's a, that's b, that's c. So it's going to be negative 3, which is 3, plus or minus b squared, negative 3 squared is 9, minus 3 times a, which is 1, times c, which is 3, all over 3 times a, which is 1. Now, let us see what happens. We have 3 plus or minus the square root of 9 minus 3 times 1 times 3 is 9. So that's 0. The square root of 0 is 0. So what we get is 3 over 3, or 1. And the y value at 1 is also 1. So we have that. We have the point 1, 1 critical point. Now, x is equal to negative b over 3. Well, negative b is negative 3 over 3. Well, that's 1 again. So the real question, and then when x is 1, y is also 1. The problem here is what is going on, because we did get critical points, max mins. At x equals 0 we did, and at our x equals 2 we did. Did I write down the right formula? And then we'll go back and find our little error. Okay, so we wrote down the correct formula and over here, and we have the right formula for the critical point. So what's going on? Okay, so I see our error. Y is equal to 1x cubed minus 3x squared plus 0x's plus 3. That is the A for the cubic, B is -3, and C is 0. C is 0. Okay, so right over here, I messed up. I didn't plug in 0. So the formula does work. You just have to use it correctly. So y is x critical point is 3 plus or minus. Well, 3 times 1 times 0 is 0. So you just get the square root of 9 over 3 times 1. Well, this is 3 plus or minus 3 over 3. Well, if you subtract, you're going to get 0. And if you add, you get 2 times 3 over 3, which is 2. We got the same two critical points as before. And we got the same point of inflection as before. Okay, let us graph this. Now first, I'm just going to cheat, and I'm going to recall that when x is 0, when x is 0, y is 3, and when x is 2, y is 1. 0, 3, 2, -1. 0, 3, and 2, -1. So the critical points are at 0, 3, and 2, -1. And the possible, I'm going to put possible point of inflection is at 1, 1. Now, for the record, every cubic equation has a critical point. But now, let's graph this. So we have the point 0, 3. We have the point 2, -1. And we have the point 1, 1. Now, all cubics either go like this or they go like that. If the max and min are on, I guess, what I would call a negative slope, they look like that. The max and min are on a positive slope, it looks like that. This is our max, this is our min. The point of inflection is in the middle. The curve has to go this way. And I didn't take derivatives. The formula already did that. All I did was to find the point of inflection. I said that x is -b over 3, so it's over 3, and b is -3, so it's -1. Go and find the y value, which happened to be 1 as well. Sorry, 1. Now, to find the critical points, I use this formula, where I replaced 4 and 2 with the number 3, the number right smack in the middle. Okay, and then I used this formula and worked out nicely. 3 plus or minus 3 over 3. I got 0 and 2. I spent a moment to find the y values, and I graphed this. All I did was go to those 3 points. I graphed my cubic with 3 points. The 2 critical points and the point of inflection. It has to go like this. There's no way it can be this type. I can't be coming down and then going up and end up down here. That one's not working. Okay, so, you just have to practice that. If these are the 2 critical points and that's the point of inflection, it has to go like that. That's where the max is to the left. You have the max and then a min. But what if you have a min and then a max and the point of inflection in between? It must go that way. So just knowing these 3 points is enough to graph a cubic. You don't have to take derivatives anymore because that formula, x is equal to negative b plus or minus, etc., it already took into account the formula. And the point of inflection formula already took it into account. Every time you have a cubic, y equals ax cubed plus a number times x squared plus a number times x plus a number, the first derivative is this. The second derivative is 6a x plus 2b, and this equals 0 when, bring this to the other side, when 6ax is equal to negative 2b, divide by 6a on both sides. Say x is negative b over 3a because 2 goes into 6 3 times. It's always negative b over 3a. One last comment or one example. If you come to know y is equal to, I don't know, 3x cubed minus 7x squared plus 4x plus 9, I can tell you the point of inflection is at, remember, that's A, that's B, that's C, and that's D. It's negative B, negative 7 over 3 times 3. A is 3. So it's just 7 over 9. Boom! I have the critical point. I didn't have to take derivatives anymore. And now go and find the y value when x is 7 over 9. Okay. This completes the video on graphing or curve sketching polynomials.